Things that you need to memorize: sine squared theta plus cosine squared theta equals to 1. Then 1 plus tangent squared theta equals to secant squared theta. And then 1 plus cotangent squared theta equals to cosecant squared theta. That's the Pythagorean identity. And then cosine sum equals to cosine minus sine. And then sine of sum equals to sine cosine plus cosine sine. Of course, when it is subtraction, you adjust it yourself. Tangent sum is sum of tangents over 1 minus tangent. Okay, that's addition formula. Implied subtraction formula. Now, double angle formula. Cosine 2 theta has 3 variations. Cosine squared theta minus sine squared theta. 2 cosine squared theta minus 1. 1 minus 2 sine squared theta. Sine 2 theta, the one we just had, is 2 sine theta cosine theta. Tangent 2 theta is 2 tangent theta over 1 minus tangent squared theta. But it's basically replacing the x and y here by theta, and that's what you will get. And then power reduction formula. So cosine squared theta equals to 1 plus cosine 2 theta over 2. Sine squared theta equals to 1 minus cosine 2 theta over 2. I actually modified that from here and from here. Maybe I use this. So this gives you this guy, and then this guy gives you this. So there's actually no new formula there. There's actually no new formula there. And then what else? Later on you will see cosine x cosine y equals to 1/2 cosine x plus y minus, actually plus, cosine x minus y. And then sine x sine y equals to negative 1/2 cosine sum minus cosine difference. Sine x sine y, sine x cosine y is 1/2 sine sum plus sine difference. What else? Oh, this one. Sum to product formula. Cosine x plus cosine y equals to 2 times that's tangent squared theta is basically from here. Let me write it down. Tangent squared theta equals to 1 minus cosine 2 theta over 1 plus cosine 2 theta. Actually, there are more. It's half angle formula. I'll go to half angle formula later on. This will be 2 times cosine half of the sum times half of the difference. Cosine x minus cosine y is negative 2 sine half of the sum sine half of the difference. Ooh, wow, Thomas, how do you memorize this? I did the proof it. That's how I memorized that. Sine plus sine equals to 2 sine sum over 2 cosine difference over 2. So sine minus sine will be 2 cosine sum over 2 sine difference over 2. Okay, that's the sum to product. Half angle formula. Let me insert that here. Half angle formula. Cosine theta over 2 is equal to plus minus, depends on the quadrant, 1 plus cosine theta over 2 sine theta over 2 equals to plus minus, depends on the quadrant, 1 minus cosine theta over 2. But these two formulas, actually from here, you apply the square root. You apply square root both sides, that's what you get. Okay. Now then, tangent theta over 2 will be plus minus square root of 1 minus cosine theta over 1 plus cosine theta. But there are more formulas for tangent. There are 2 more variations. There are 2 more variations. Oh, what happened? Why doesn't it move? Give me a second. So for tangent, another one is 1 minus cosine theta over sine theta. The other one is sine theta over 1 plus cosine theta. Okay, let me see, I have a message coming in. Since this is a lot to remember, will you hint to use this formula in the test? No, you have to know this. You have to know this. This is not a lot if you have memorized that since your trigonometry class, which is 1.5 years ago. If you try to memorize that last minute, of course, do it at your own risk, right? But no, you are in calculus 2. You are in calculus 2. Okay, but don't worry, we will actually get into all these formulas slowly, not all at once. But in your test 1, which is, I think, 2 weeks from now, approximately 2 weeks from now. So you still have 2 weeks to memorize this, okay? Then you will be, I do expect you to memorize this already, okay? Well, then remind yourself, you still have 2 weeks. It's like, I'm telling you now so that you actually start memorizing it from now, okay? I'm not telling you 1 day before the test. Of course, that's too much, right? But you don't tell me that right now that you don't memorize it, therefore you will forever not memorizing it. No, I'm telling you now so that you have time to study. Okay? Anyway, coming back here, so when u equals to pi, cosine pi is -1. Then this becomes integral from 1 to -1. Remember, once you do substitution, the limit of integration should also change at the same time. At the same time. Okay, this is e to the u times 2 u negative du. Okay, I take the 2 out and I will reverse the limits of integration by absorbing the negative. U e to the u du. So you see, so far I don't do any integration. I just do modification, substitution and simplifying. Then from here, I do my integration by tabular method. This is 1, oops, that's 1, this is 0, e to the u, e to the u. So this is equal to 2 u e to the u minus e to the u from -1 to 1. That is equal to 2 times, when it is 1, that's e minus -1 e to the -1 minus e to the -1. That is 2 times 2e to the -1. That's 4e to the -1. So that this is now taking the place of the integration. That's for number 40. Let's say number 42. Integral of sine of natural log of x dx. I know integral of sine u, so let me use u equals to ln x. So du equals to 1 over x dx. But hold on, I need to solve x by itself. So x du equals to dx. But if u equals to ln x, what will x be? E to the u, right? So this is e to the u du equals to dx. So now that integral becomes integral of sine u times e to the u du. Oh shoot, this is the trigonometry and exponential. Oh, it seems like we need to do the folding later on. Let's do it. So the derivative of sine is cosine. The derivative of cosine is negative sine. Integral of e to the u respect to u is e to the u. Okay, so that is equal to sine u e to the u. Maybe actually I prefer to write it down. E to the u sine u minus e to the u cosine u minus integral of sine u times e to the u du, which is what we have originally. Okay, if we call this our I, if this is our I, then this is an I also. Okay, so 2 times I, which so 2I equals to e to the u sine u minus e to the u cosine u plus constant. So the I will be 1/2 e to the u sine u minus 1/2 e to the u cosine u plus another constant. So the integral of sine of ln x dx is equal to 1/2 x sine ln u, ln x minus 1/2 x cosine ln x plus a constant. Now there are formulas that I think we will do a lot, especially in the next section. If not the next section, it will be the next section, that you may want to kind of like, in some sense, memorizing. Okay, for example, integral of, even though this is not the way I would like you to do it though, but somebody from last year actually memorized it this way. Integral of sine squared dx, prove that this is equals to x over 2 minus sine 2x over 4 plus constant. Proof. I don't think that's how I will do it though. Well, okay. Proof. Without integration by parts. I think if I do it without integration by parts, I will use the power reduction formula that we have above. I use power reduction formula that I have above. Here, I will use this one. Okay, I will use that one. And this is 1 minus cosine 2x over 2 dx, which is integral of 1/2 dx minus integral 1/2 integral cosine 2x dx. This will be x over 2 minus 1/2 times, from that integral I get another 1/2 sine 2x plus constant. I believe this is not what I have in mind. This is part A only from number 47. Number 47, part A. Now the thing is, how do we use this? How do we use this to prove part B, to show part B? Then how do we use this to show integral of sine to the fourth x dx? How do we do this? So this is integral of sine squared x times 1 minus cosine squared x dx. And this is equal to integral of sine squared x dx minus integral of sine squared x cosine squared x dx. Now, this part here already done. This part here is already done. We get that's equals to x over 2 minus sine 2x over 4 plus constant. But I still have integral, so I don't need it. While the one on the right, the second term here, I will make it like this. 2 squared sine squared x cosine squared x over 2 squared. Now the purpose is because I want to get double angle squared on the top. They actually give us this in the reduction formula that they did earlier in example 6 according to number 47. But I basically redo it from the beginning. This is x over 2 minus sine 2x over 4 minus 1/4 integral. This is sine squared 2x dx. Then you can integrate that again. Actually, we see that this will be, I copy this part here, minus 1/4. Now, I wonder if you remember, we have the integral of sine squared earlier, right? The integral of sine squared of x is this thing. Now, what happened if you replace that x by 2x? What happened if you replace that x by 2x? Then you will have the 1/2 times 2x over 2 minus sine of 2 times 2x. So you replace x by 2x. So we will get x over 2 minus sine 2x over 4 minus x over 8 plus, what is this? 1632 plus sine 4x over 32 plus constant. Actually, I can combine my things here. Plus 3x over 8 minus sine 2x over 4 plus sine 4x over 32 plus constant. Number 51 to 54 are gems. I would like you to actually try those at home. One of the assignment I will give you sometime before the test one. Maybe on Wednesday I will give it to you. It's to do proofing of those integration formulas you can find at the back of your book. If you go to at the end of your book, at the cover, you will see reference page 6, table of integrals. If you have your textbook, you can take a look on reference page 6 at the back of your book. The very, very back, very far to the end. Then you have table of integrals from 1 to 120. I don't need you to, I will not ask you to memorize all of them. Yeah, I will not ask you to memorize all of them. Let me show you. Yeah, let me show you. This is the book, right? This is the book. Okay. Now, at the end of the book, okay, at the end of this book here, sorry, it's heavy. So it ends here. It ends here. Okay, it ends here. But it actually starts from, I believe, from here. Okay. Now, at the end of this semester, I expect you to be able to prove all 120 of them. That's why I emphasize heavily on technique of integration. Okay. I have 2 chats coming in. Did you say quiz on Wednesday? No, I plan to give you a take-home quiz on Wednesday. Just like your quiz, the one that you turned in last week, I guess, right? Right. I have not started grading it. I plan to do it tonight. Yeah. So on this Wednesday, I will give you a quiz that is due on Monday next week. Okay, let's say, for example, we take a look on number 52. I think even number 51 should not be in the book because it's a proofing, right? But anyway, I need you to get used to it though. I need you to get used to it. So number 52, integral x to the n e to the x dx. And the question is proof that this guy is equal to x to the n e to the x dx, I'm sorry, no dx, e to the x minus n times integral x to the n minus 1 e to the x dx. The proof will be, we do integration by parts, x to the n e to the x dx. The derivative here, oh, give me a second. Give me a second. Let me continue. Then this part here, I do the derivative. This part here, I do integral. So this is equal to this guy, which is x to the n e to the x minus, because I do this horizontally, then I have integral of n x to the n minus 1 e to the x dx, which is basically what we need. Now let's do the hard one, number 54. Number 54, we have integral of secant to the n dx. The question is prove that this is equal to tangent x secant to the n minus 1 x over n minus 1 plus n minus 2 over n minus 1 integral secant to the n minus 2 of x of x for n not equals to 1. Proof. Yeah, I forget the x. Secant to the n of x. Okay, the proof, I start with secant to the n of x dx. I will rewrite that as integral of secant to the n minus 2, maybe secant squared first. Secant squared of x times secant to the n minus 2 x dx. Thomas, why do you write it that way? Why do you write it this way? Because of, I break it up. I break it up this way because I know the integral of secant squared is tangent. Right? The integral of secant squared is tangent. Maybe I rewrite it backward then. Integral of secant to the n minus 2 of x times secant squared x dx. Then the derivative here will be, the left-hand side, the derivative will be n minus 2 times secant to the n minus 3 x times, what is the derivative of secant? Times secant tangent? While the integral of secant squared x is tangent x. Now then, I get this guy, which is tangent x secant. Why I get something right? Oh, yeah, I copied wrong. So this one here should be n minus 2. So this is n minus 2x, that's for the yellow one, minus integral of n minus 2 secant to the n minus 3x times secant x tangent x times tangent x dx. What the heck? There's a long part, huh? Yeah, you need to be patient though. Then go on further, tangent x times secant to the n minus 2x minus n minus 2 here. And then I have integral secant to the n minus 2 tangent square x dx. But then I will break that later part as this is secant to the n minus, I forgot the x again, to the n minus 2x, and then secant squared x minus 1 dx. Y to the power of n minus 3 becomes n minus 2 because of this. This guy times this guy. If you this guy. It's just like this guy here becomes this. Okay, which if I go on further, this is basically what happened here. From here becomes this. Okay, I go on further. This is tangent x times secant n minus 2 of x minus n minus 2, and then this is integral secant to the n of x minus dx minus integral secant to the n minus 2 of x dx. Wow. I will distribute the n minus 2, that's tangent x secant to the n minus 2x minus n minus 2 integral secant to the nx dx plus n minus 2 integral secant to the n minus 2 of x dx. Now the thing is, on the left hand side you actually have secant to the n of x dx, right? Which is the same guy with this. Okay, so if I move it to the left, then I will get, if I call this I here, this will be I here. Then I will get I plus n minus 2 of I equals to tangent x secant to the n minus 2x plus n minus 2 times integral secant to the n minus 2x dx. But the left hand side is n minus 1i. So I is equal to, let me write it completely. That's tangent x secant to the n minus 2x plus n minus 2 integral secant to the n minus 2x dx. Now divide by n minus 1, we get what we need. Heavy, huh? Yeah, you need to do those though. Okay. Suggested homework will be from the 7.1b will be from number 37 to number, you should try up to number 65, I guess. Just do the odd ones. How did that n minus 2 becomes n minus 1? This guy here, you combine like terms. 1i, so 1 plus n minus 2 is n minus 1. Okay? Actually, I would like to do one more problem, something that's, as I remember, this is quite useful in future in your differential equation, number 50. Number 50. Prove that for n equals to even, prove that integral from 0 to pi over 2 of sine to the 2n of x dx, prove that this is equal to 1 times 3 times 5 all the way to 2n minus 1 over 2 times 4 times 6 and on. This is 2n times pi over 2. The work here actually coming from, number 49. Yeah, the work here actually coming from number 49, where they do power reduction. Now, let's prove that first. Prove integral from 0 to pi over 2 of sine to the 2n of x dx I will make it like this. Integral from 0 to pi over 2 of sine to the 2n minus 2 of x times sine squared of x dx. Is it okay? So I take sine squared x out. And then I modify this to be sine the 2n minus 2 of x of 1 minus that's 1 minus 4 sine squared x dx. Which is equal to integral from 0 to pi over 2 of sine to the 2n minus 2x or times dx minus integral from 0 to pi over 2 sine 2n minus 2 x cosine squared x dx. Notice that the exponent here, is already exactly 2 less than the exponent here. Okay, it's exactly 2 less than the exponent there. My problem is, how do I integrate this? Let's do integration by parts. How would I like to do this? Integral. Let me rewrite it first. So this is equal to integral from 0 to pi over 2 of sine n minus 2x dx minus integral from 0 to pi over 2 sine to the 2n minus 3x or sine squared x sine x dx. So I pull one of the x to help me to integrate the one on the right hand side later on. Let's hope that this works. So the derivative on the left hand side is 2n minus 3 sine to the 2n minus 4x times cosine x. While on the right hand side, this is negative 1/3 cosine cube. I'm sorry, yeah, cosine cube. X. Why I feel like this is not what I want to do. You know what? No. This is not what I want to do. Sorry. Erase it. Because it's actually harder to integrate this later on. Sorry. I don't need this. Actually, it's the other way around. 2n minus 2. So I write the cosine here. And then sine to the 2n minus 2x cosine x dx. So to be more precise, what I did is I break this cosine x here. Cosine squared x becomes this guy and this guy. Now I do the derivative. So the derivative here will be negative sine x, while the integral here will be negative 1 over 2n minus 1 sine 2n minus 1 of x. Do I have plus or minus? I don't need negative. which means this is integral from 0 to pi over 2 of sine to the n minus 2x dx minus cosine x times sine to the 2n minus 1 of x over 2n minus 1 plus integral of 1 over 2n minus 1 of sine to the 2n of x. Ooh, wow. But this is supposed to be from 0 to pi over 2, from 0 to now notice that on the left hand side I have integral from 0 to pi over 2 of sine to the 2n dx, which is, let's call that I. This is also I. So I minus 1 over, actually becomes plus, becomes plus 1 over 2n minus 1 I, this guy here, together with this negative, go here. So equals to integral from 0 to pi over 2 sine 2n minus 2x dx minus 1 over 2n minus 1 when x equals to 0. So this is 0. When x is pi over 2, that's 0, minus when x is 0, that's also 0. So basically, what we get here is, if I combine my terms, that's 2n over 2n minus 1i equals to integral from 0 to pi over 2 sine to the 2n minus 2 of x dx. So the I, which is integral from 0 to pi over 2 of sine to the 2x dx of x dx equals to 2n minus 1 over 2n integral from 0 to pi over 2 sine to the 2n minus 2 of x dx. Wow, Thomas, that's all you get? Yeah, that's all I get so far. But then if I go on further, this is the same to 2n minus 1 over 2n integral from 0 to pi over 2 of sine of 2 times n minus 1 dx of x dx. So that is 2n minus 1 over 2n times 2 times n minus 1 over 2 times n minus 1 integral from 0 to pi over 2 of sine 2 times n minus 2 dx. So you see, I will do it recursively. I will do that recursively. This guy here will be 2n minus 5 over 2n minus 4 integral from 0 to pi over 2 of sine 2 times n minus 3 of x dx.
Wait, I didn't understand the previous step.
The one from here to here?
Yeah.
Okay, so we already have this. We already have this guy here, right?
Yeah.
Okay, now do substitution for this. Do substitution for that. Change the n minus 1 by call that u. So what is the integral from 0 to pi over 2 of sine to the 2u of x dx? That will be, according to the formula we have earlier, that will be 2u minus 1 over 2u integral from 0 to pi over 2 of sine to the 2u minus 2x dx.
Okay, that makes sense.
Okay, so I keep on using the same formula again and again.
Mm-hmm.
I keep on using the same formula again and again until they did say that even power of sine. Oh no, so they didn't say that the n is even. My bad. I need to change this. 2n is even. 2n is even. Okay, so you will see eventually if 2n is even, so this is 2n minus 1, this is 2n, and you see the numerator is 1 less than the denominator. Eventually, until you get, for example, 5 over 6, 3 over 4, 1 over 2, is it right? Okay, but the last one will be integral from 0 to pi over 2 of sine squared x dx. Which I think will give us 1/2. You see that? No? Let me see some pattern. Let me see some pattern. This is 2 times n minus 2. So that's less. Okay, no. Up to, only up to here. Only up to here. Only up to there. Down to there, that's right. And this is 2n minus 1 over 2n, blah, blah, 5 over 6, 3 over 2, and then the one inside here, that's 1 minus cosine 2x over 2 dx. I bring the 1/2 out, so I get integral from 0 to pi over 2 of 1 minus cosine 2x dx. And you will see that in this domain of integration, this would be 0. Okay, therefore this integral here is pi over 2. Now I will rearrange this. I will rearrange this to be 1 over 2, 3 over, I'm sorry, it should be 4. It should be 4. 3 over 4, 5 over 6, all the way to 2n minus 1 over 2n times pi. So if I combine the numerator together, that will be 1 times 3 times 5 up to n minus 1. On the denominator, we will have 2 times 4 times 6 up to n times pi over 2. Some little note. I think I would like to mention this note. Integral from a to b of a constant dx is equals to c times the length of the interval. Do you agree? You have two ways to actually think about this. One way to integrate that as usual. This is c times x from a to b. That's c times b minus a. Another way to look at that is, you see, if you have a constant function, from a to b, what is the area under that constant function? Okay, so the area here will be, the area here is the same to that thing, right? Does it make sense for you for this part? Okay, so Thomas, how do you compute, like it seems like you did it visually, integral from 0 to pi over 2 of cosine 2x dx. How do you get that so fast that it is equal to 0? Let me answer this first. Before I answer that one, integral from 0 to pi of cosine x dx. You can just integrate this though, okay? Yeah, you can just integrate this. You said this is sine x from 0 to pi, and that will be 0 minus 0, that's equals to 0. Do you agree? Okay, that's a very textbook method, nothing wrong with that, but you still need to work it out. The way I think you should think about it is this. Take a look on the graph of cosine. The graph of cosine from x equals to 0 to pi, and then from pi to 2 pi. Now the thing is, the area here and the area here are the same, except that the value are opposite. So when you take the integral from 0 to pi of cosine x, it's supposed to be 0. In fact, if you compute that, you will see this, the area here is 1, the area here is negative 1. So when you add them, it should be 0. Can you follow me so far? Now, what happened to this case here? What happened to this case here? Now, that case there is the graph of cosine 2 pi is, you shrink that by factor of 2 on that cosine x. So the period now is pi. This is pi over 2. Now the integral you did there is basically getting the area under the curve, quote unquote, here and here, which we know is supposed to be the same size. I think the size is 1/2 for each of them. So the size here is 1/2, the size here is -1/2. But when you add them, it's supposed to be 0. Now with that mindset, especially this one, I really think you should memorize this to the point of memorizing integral from 0 to pi over 2 of sine x dx is equal to 1. Now, with that, what can you say about integral from 0 to 5 pi over 2 sine x dx? This is integral from 0 to 2 pi sine x, that's one period, they cancel each other, plus integral from 2 pi to 5 pi over 2 sine x dx. That's equals to 0, that's equals to 1. But what I did here is more into the understanding of how the integral works. You see that integral as the area under the curve. Okay, anyway, I'm done with what I need to prove here. I really need to stop. Otherwise, I keep on working on proving that proving is fun. That's the thing. I know you don't like it until you, but proving is the way for you to build your mathematical intuition. Okay, I think I give you the suggested homework already. Yeah, from 37 to 65. Right now is 8:36. Let's take a break. So let's take a break to 8:50. Now, when we get to 8:50, then I will go on to 7.2. Okay, see you later. In this 7.2, we will discuss 3 types of trig integrals. Trigonometry, integrals. The first one is the sine x to the n cosine n to the n of x. So cosine sine type. The second type is tangent secant type. Yeah, we will only do those 2 parts. And then, the third one is when we have sine ax cosine bx type. But for this last one here, we will use the formula that I gave you earlier. Something to do with this. We will use this. Okay, for this 7.2. Now let's start with the sine cosine ones. Sine to the m of x cosine to the n of x. Now I will do some examples first. And then we look back to the strategy. I will use integral dx here. integral dx here, integral dx here, so that you know that we are talking about cases in integral. Now, for example, give me a second. Okay, suppose I have, for example, integral of sine cube x dx. The plan is the following. I need one either sine or cosine to help me with the substitution. So I will break this into sine squared x sine x dx. Now this can be used as for our du later on. That can be used for my du, and therefore this has to be expressed in terms of cosine. So this is integral of 1 minus cosine squared x sine x dx. Is it right? And then I do substitution, u equals to cosine x du equals to negative sine x dx. So this becomes integral 1 minus u negative du. Which give us negative u plus 1/2 u squared plus constant. That's 1/2 cosine squared x minus cosine x plus constant. I'm sorry, it should be squared here. This should be squared here. So this should be cubed by 1/3. So yes, if the sine have odd exponent, you pull it out. In fact, that is true even if one or both of the sine cosine are odd. Let's say, for example, integral of sine cube x cosine to the 6x dx. Then I will rewrite this as sine squared x cosine to the 6x sine x dx. So one of the odd one is the one you pull out to help you with the substitution. Okay, so I will write this as 1 minus cosine squared x cosine to the 6x sine x dx. We use the same substitution, u equals to cosine x. Du is negative sine x dx. Then it becomes integral from 1 minus u squared u to the 6 negative du. So that's equals to 1 over 9 u to the 9 minus 1 over 7 u 7 plus constant, and then from there we substitute that back. Okay, now notice that this work here in example 2 does not really change even when the cosine has odd exponent. So if you have both of them odd, then you can pull either one of them. Okay, but what you need is actually only one odd exponent. We just need one odd exponent to pull out to help us with the substitution later on. Okay, so the summary we can get from here is, first, if m or n equals to odd, then pull or factor out for du. Now the thing is, what happens if both of the exponent is even? Example 3, let's say if I have integral of, let's say if I have integral of sine to the fourth x cosine squared x dx. So we are basically doomed. What we will do is we use double angle formula. Sine squared x equals to 1 minus cosine 2x over 2. Cosine squared x is 1 plus cosine 2x over 2. Or you can also use sine x cosine x equals to 1/2 sine 2x. Again, you can find this formula in the list I gave you earlier in 7.1. So for this guy, for example, I will redo this as, this is 1 minus cosine 2x over 2 being squared. As for the sine to the 4x, yeah, the guy inside the parentheses is sine squared. So I squared it again. While this guy here, becomes 1 plus cosine 2x over 2. This is now equal to 1/8. A 2 squared times 2 on the denominator, that becomes 1/8. Okay, and then integral, I will FOIL that, but I hope you can see that one of the factor is, let me write it as 1 minus cosine 2x, 1 minus cosine 2x, 1 plus cosine 2x. Is it right? On the top, that's what it becomes. Now the thing is, the product of this is a nice thing. Or basically you need to FOIL it. Okay, basically you need to FOIL it. So this is 1 minus cosine 2x times 1 minus cosine squared 2x dx. But that is, this is sine squared 2x dx. Right? Yeah, I know it's painful. Let's go on. This is equals to 1/8. I will separate them. Integral sine squared 2x dx minus 1/8 integral sine squared 2x cosine 2x dx. Now, the thing is, for this one here, I cannot really integrate it right away. Then I do double angle again. So 1/8 times 1/2 integral 1 minus cosine 4x dx. Well, this part here, I do substitution. U equals to sine 2x, so du will be 2 sine, I'm sorry, 2 cosine 2x dx. Or cosine 2x dx is 1/2 of u. So this is minus 1/8 times 1/2 integral u squared du. 1/2 du is this 1/2 du. Absorb the cosine 2x dx. Then I get 1/16 integral of 1 is x, integral of cosine 4x is 1/4 sine 4x minus 1/16 times 1/3 u cubed plus constant. This is equals to 1/16x minus 1/64 sine 4x minus 1/48 sine cube of 2x plus constant. Now, anything else for sine, cosine is basically variation of this. And let's try doing problem from our textbook. Doing problem from our textbook. Let's say I do number, I want to do number 6. It's too easy. Number 8. Integral from 0 to 2 pi of sine squared of theta over 3 d theta. Do substitution first. So u equals to theta over 3. So du is 1/3 d theta. I have a message coming in. Which one? I don't get them. Shouldn't it be 1 minus u squared? Should that be 1 minus u squared? Let me see. Is it right? For the last one you're talking about? I don't think so, because this is my u. This is my u. This is my half du. Yeah, correct me if I'm wrong though, but in this case, I think I'm fine. Let me see. Did I make any mistake? Which one? Okay, well, anyway, I'll get a wrong message, I guess. Something earlier. So, so this will be, oops. So 3 du equals to d theta. And actually u0 will be 0, u2 pi will be 2 pi over 3. So the integral now becomes 0 2 pi over 3 sine squared u 3 du. And is it sine cube? Yeah, that's sine cube. Okay, so actually this one is no fun. Oh, this is 3 times integral from 0 to 2 pi over 3, 1 minus cosine 2u over 2 du. So integral of 1 is u, integral of cosine is negative cosine is negative sine. So this is 3 over 2, 2 pi over 3 minus 1/2 sine 4 pi over 3 minus 0. I'm sorry, radical cube. This is pi plus 3 radical 3 plus 8. But I have to be honest with you, nothing fun here. How about number 16? Ah, that one seems to be interesting. Number 16. Integral of x sine cube x dx. To integrate sine cube, I don't think I can do it directly. Should we do it separately? I think so. Okay, let's try. So solution. Consider integral of sine cube x dx. Later on, I need to do integration by part for this question here. I need to do integration by parts, this guy and this guy. But for me to do so, I need to integrate this sine cube, which I think takes some time. So that's why I do it separately. That's equals to integral of sine squared x sine x. I somehow think I did this already in my first example. Can I just code it? Yeah, that's what I have. So, going back, integral of x sine cube x dx. Do integration by parts. This is 1, this is 0, this is 1/3 cosine cube x minus cosine x. Is that what I want to do? Seriously, times? This is what I really want to do. So this is equal to x times 1/3 cosine cube x minus cosine x minus integral of 1/3 cosine cube x plus minus cosine x dx. No, I didn't expect it to be that ugly. My bad. So x cosine cube x over 3 minus x cosine x minus 1/3 integral of cosine cube x dx plus integral of cosine x dx. The last one is easy. That's just sine. Oh man, I need to do this again. I really don't want to do this stuff. Anyway, there must be another way to do it better. So let my u equals to sine x, so du equals to cosine x dx. Minus 1/3 integral of 1 minus u squared u I'm so lazy to write it, so I just do it. But u, oh, by the way, I can combine this thing. Huh? I can combine this thing later on, so it becomes, so it's, okay. So x cosine cube x over 3 minus x cosine x plus 2/3 sine x plus 1/9 sine cube x plus constant. Ooh, that's a long one. I wonder if there's another way to do this. I wonder if there's another way to do that. Let me try another way. This is integral of x sine cube x dx. I will make it integral of x sine x 1 minus cosine squared x dx. I wonder if that helps more. Well, basically, then I make it into two integrals. This first part here, I can easily do integration by parts. The second one is the one I don't know. I wonder if this will help. Nah, it doesn't help. Well, anyway, let me show you why. I still have the same issue on the second part of the second term. This is y. This is negative cosine x. This is 0, negative sine. So this is negative x cosine x plus sine x. So the one here, this is 1. The integral of this will be negative cosine cube x over. So this is minus negative x cosine cube x over 3 plus 1/3 integral of cosine cube x dx. But yeah, I still have the same trouble here. But you notice that at least that you should go on, of course. At least that this part, the plus positive x cosine cube over 3 is this. This part here is this. Okay? And this part here is this. And from this integral, get from there. Seems like I have no way to avoid that. Doing that cosine cube. Thomas, don't you feel tired? I'm tired. But I'm not tired because of the integration. I'm tired because I've been working since basically 10 o'clock in the morning. Why I want to say this to you? You may feel that you get tired at this time, at this moment, because you do too much integration. But I would like you to know that's actually part of the training you're supposed to get. The reason you are now in Calculus 2, because you need integration in future, and there are a lot of them that you need to do. Now here and there, I try to teach you a little shortcut. Like for example, remember this one integral. Let's say if I get integral from 0 to 3 pi over 2 of sine x dx. What is this equal to? This is equal to 1. Why? Because of this. Sine x looks like this. The area per quadrant is 1. This is -1. But if you need this guy and this guy and this guy, then the total area should be 1. Okay, so one way to do that problem is by imagining what the graph looks like and what happened to the area under the curve. Then let me use dot 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 here, but then you will get the answer the same down. Now that's for sine cosine style. How about tangent and secant style? Part B, integral of tangent to the n of x secant to the n of x dx. Let's remember the following. If our u is tangent x, then our du is secant squared x dx. At the same time, secant to a squared x is equal to 1 plus tangent squared x. Okay, now from here, I hope then you realize that we would like secant to the even power. Why? Because I can pull 2 of the secant, like secant squared out. Okay, and the remaining becomes in terms of tangent. Let's say, for example, integral of tangent cube x secant to the 4th x dx. So my point is this. I can break this into secant squared x secant squared x dx. Is the audio off? Can you hear me? Okay. So I guess it's just that one time. Maybe that one time. Okay, now then my plan is this. If I let my u equals to tangent x, my du will be secant squared x dx. So this will be my du. This is my u cube. right? And I can still massage this in terms of u. Okay, let me use different colors for each one of them. So this is my blue color. This is my green color. This is integral u cubed. This is 1 plus u squared, right? And this is du. Now all of a sudden it becomes polynomial. Integral of u cubed plus u to the 5th du. 1/4 u to the 4th plus 1/6 u to the 6th plus constant, and then you substitute that back. Tangent to the 4th x over 4 plus tangent to the 6th x over 6 plus constant. Now what happens, Thomas, if the secant is odd? Then pray hard that the tangent also odd, because the second plan we have is the following. If u equals to secant x, then du equals to secant x tangent x dx. Okay, so if you have, for example here, integral of tangent, maybe I make a tangent to the 5th x secant cube x dx. Now my plan is I will take one tangent, one secant aside. Will help me with my substitution. Okay, so let u equals to secant x, then du will be secant x tangent x dx. This will be my du. This will be my u. And I have to massage this. Okay, let me rewrite it first. This is integral, for the first part, this will be secant squared x minus 1. That's tangent squared, being squared, and make it tangent to 4. So I get integral u squared minus 1 squared u squared du. Now it is a polynomial. Integral of u to the 4th minus 2u squared plus 1 times u squared du, u to the 6th minus 2u to the 4th plus u squared du. That's u to the 7 over 7 minus 2 over 5u to the 5th plus 1/3 u cubed plus constant. Then you substitute that back. Now the thing is, in case of secant and tangent, however, there is no, oh, by the way, this happened to be number 28. Oh, good. So I did problem from the book. Now, in case of secant tangent, you will see we have some case where it's actually not, how to say it, it's not easy to do. It's not easy to do. In this case, if the secant is odd and tangent is odd, then you can bring them out. You can take one tangent, one secant, and this becomes even. Now, once both of them even, then you can change the tangent in terms of secant. Tangent squared in terms of secant squared. Now, what happens if, unfortunately, this is even and this is odd? Let me show you. We are about to do something that I myself get scared when I try. What happens if we have integral of tangent square x and then secant x dx, for example? Or basically, if this is even, let me change this to even, and this one is odd. How do we do this? That would be difficult. That would be difficult. But to prepare us for that kind of question, with that kind of question, we need to develop some important integration. The first one, what is the integral of tangent x? What is the integral of tangent x? Now, we did that before. I hope you still remember. But this is a little substitution here and there. This is natural log of secant x dx. Secant x plus constant. How about integral of secant x dx? This is natural log of secant x plus tangent x plus constant. Let me prove it. The proof of this integral of secant x directly is actually coming from somebody. You can see this in your book on page 499. But we actually have done this backward. We already proved that the derivative of this is equals to that. We already proven that the derivative of natural log of secant x and plus tangent x is secant x. And we have done that in chapter 6. But now I want to prove from left to right. So integral of secant x dx is equal to integral of secant x times secant x plus tangent x over secant x plus tangent x dx. So I multiply by 1 in that form, which is equal to integral of secant squared x plus secant x tangent x over secant x plus tangent x dx. And then we realize that if my u is the whole denominator, then my du will be the whole numerator. So this is integral of du over u, which is natural of absolute of u plus constant. Memorize this one. Okay, both of these memorize. Memorize both of these. But there's one more integral that is showing up a lot in our calculus 2, quite often, such that, especially in chapter 7, such that I would recommend you to memorize this. As I remember, it shows up a couple times also in chapter 8 and chapter 10, as I remember, which is integral of secant cube x dx. Now, I need you to memorize this one though. Okay, this is 1/2 secant 1/2 secant x tangent x plus 1/2 natural log of absolute secant x plus tangent x plus constant. I think after I prove this, then I will do some problem from our textbook. And then I'll let you go. Proof. The proof is in the book, but I want to go over this because it's so important. Integral secant cube x dx is equals to, we will break it up this way, secant x times secant squared x dx. And then we do integration by parts. The derivative of secant x is secant x tangent x. The integral of secant squared x is tangent x. So that integral now is equals to tangent x secant x. Let me forward it, secant x tangent x. Secant x tangent x, that's for this part. Okay. Minus integral of secant x tangent squared x dx. Horizontally, we keep the integral sign. Okay, that's the yellow. That's the blue. Now the thing is, the second part, the second term, can be rewritten into secant x times secant squared x minus 1 dx, right? Minus integral of secant cube x plus a dx plus integral of secant x dx. Now notice that on the left hand side is our I, integral of secant cube x. So I will move this term here to the left. I get 2 times integral secant cube x dx equals secant x tangent x plus integral of secant x is natural log of secant x plus tangent x. Don't forget plus constant. Now then we divide by 2. So let's take a look on, for example, number 32. when things get tough, integral of tangent squared x secant x dx. Now, if you memorize those three formulas here, if you memorize these three formulas here, especially formula number 2 and number 3, then this question will turn out to be an easy one. It's integral of secant squared x minus 1 for the tangent squared x, for tangent square x, and then secant x dx stay outside. Now this becomes integral of secant cube x minus secant x dx. You can integrate them one by one right now using formula number 3 and formula number 2. I think at the end you will get negative 1/2. No, positive. That's 1/2 secant x tangent x minus 1/2 natural log of secant absolute secant x plus tangent x plus constant. Number 34. Integral of sine phi c. C cosine cube. Is it C or phi? I think that one is. I don't know. How do you read? I can rewrite this into integral of tangent phi times 1 over cosine squared and secant squared. That's Theta. Oh, this one is easy. And u equals to tangent phi, right? So the u is secant squared phi dphi. Ah, that's Mickey Mouse. This is integral of u du dot. That's 1/2 u squared plus constant. That's 1/2 tangent squared phi plus constant. No fun. How about number 36? Ah, something new. What is new is not with that, with this. It's not new here. This is not new. The new one is the cotangent. How do we deal with cotangent cube x dx? How do we deal with cotangent cube x dx? So u equals to, if I by u is equals to cotangent x, by my du will be the derivative of cotangent is negative cosecant squared x dx. Is that right? I think it's negative. So cosine x over sine x, when we do the derivative, that will be, I don't remember this on the top of my head, that's why I just do it again. Sine squared x here. So negative sine squared x minus cosine squared x. Yeah, that's right. That's negative 1 over sine squared x. That's negative cosecant squared x. That's right. Now, then at the same time, we also know that we will use this later on. Cotangent squared x plus 1 equals to cosecant squared x. Okay, so I will break it up this way. This is pi over 4 to pi over 2. The cotangent squared will be cosecant squared. What about it? Yeah, so that would be cotangent x times cosecant squared. It would be cosecant squared x minus 1 x. This is integral from pi over 4 to pi over 2 of cotangent x cosecant squared x dx minus integral of cotangent x dx. Now then I will, how about this guy here? What is this integral? What is the integral of cotangent? Natural log of sine. Right? Now the thing is, for this guy here, I need to do that kind of substitution. I will do this kind of substitution here. So I get integral u negative du. Now cotangent pi over 4 is 1. Cotangent pi over 2 is 0. So this is integral from 0 to 1 u du minus natural log of sine x from pi over 4 to pi over 2. I'm sorry, I'm over time, but and go on. This will give me 1/2 minus natural log of 1, which is 0, minus natural log of radical 2 over 2. That's equals to 1/2 minus 0 plus, this is natural log of 2 to the power of negative 1/2. So this is 1/2 minus 1/2 natural log. Your suggested homework from here for 7.2 will be a lot of practice though. Okay, number 1 to number 47, I guess, is good enough. Let's do the odd ones. Now, I don't expect you to have done all this 7.2 on Wednesday, but do at least do every other odd. Okay. Now then on Wednesday, I will go on with 7.3. We will spend quite some time there. But we are done with our test 1 material actually on 7.3. 7.4 will be in your test 2 instead. Okay, that's for today.